if someone walked up to you and I and they said, hey, can you tell me about the difference between a VNIC and a VMNIC? Or perhaps they were asking about a VM kernel port or an uplink or a VM port group. Wouldn't it be great to be able to go ahead and answer all of those questions directly and accurately? Well, in this nugget regarding the concepts regarding vSwitches, you and I are going to take a major step in that direction. I'd like you to do me a favor. Think back to when you first started learning about networking, when it was first starting to make sense to you. Now, those were exciting times, whether you started learning about networking 10 years ago or 20 years ago or even a year ago. The concepts and the tinker toys and the building blocks that go into networking are fascinating. And it's equally exciting when we start virtualizing the network components as well. So to understand a vSwitch, a virtual switch, let's first take a look at a traditional layer 2 switch to take a look at how it works. So in our network topology, let's say this represents Acme Incorporated's headquarters site. And let's go ahead and focus right here on switch number 2. Now, connected physically into this switch, we have these computers. Here we have computer 2, here we have an internal server that are connected very likely with unshielded twisted pair cable to individual ports on the switch. So as far as the ingredients to make all this work, the computers have NICs, which is an acronym for Network Interface Card. And burned into those network interface cards, there's a 48-bit layer 2 MAC address that uniquely identifies that card on the network. Now, by default, a layer 2 switch is one giant layer 2 broadcast domain. And you might say, well, Keith, what exactly does that mean? Well, if a computer sent a layer 2 broadcast, let's say an ARP request or some other broadcast traffic for IPv4, if it goes into the switch, by default, the switch is going to forward that broadcast to all other ports on that switch. Now, in most environments, we don't want to have just one giant broadcast domain, one giant network. So what we do is we take ports on a switch and we carve them up into groups of ports. And the benefit of doing that, we could have, for example, 2 or 3 ports as a member of one group and some other ports as a member of a different group, and then we could treat them differently. For example, one group of ports might be VLAN 20 and another group of ports might be VLAN 30. Or maybe we're doing some quality of service and prioritization of traffic, and we're giving one group of ports better throughput and less restrictions than another group of ports. So for example, here on switch number 2, maybe we have 3 different groups of ports. Let's say we have one for production, one for test and development computers, and one, for example, for human resources. So we'd simply make sure that when we connect a computer to the switch, that the port that computer is connected to is associated with the correct group, if you will, of ports. Another factor that I can see here in our topology is that we have some connection to external systems. For example, there's a connection right here between switch 1 and switch 2. So we could consider that an inter-switch connection. We could refer to it as an uplink. So basically, it's a physical port on one device connected to a physical port on another device, allowing communication between the two. We also have another path outside of this switch that goes over to router 1 with this little connection right here. That's another example of an external connection that goes off to points beyond. And that's another big component as a part of traditional networking. So we have external connections. And I'll put a slash uplinks. Now, if these switches here are simply layer 2 switches, they don't have any routing capabilities, meaning they can't route based on the layer 3 IP address inside of a packet. So there's a couple solutions to that. Number one, you can get a multi-layer switch that does the routing, or you can go ahead and have a connection to a layer 3 routing device, like this hockey puck looking thing right here, which is router 1. And if we did have multiple groups of ports in different VLANs, this link between the router and the switch is very likely going to be set up as a trunk. And a trunk simply allows the switch, for example, if it has VLAN 10 and VLAN 20 and VLAN 30, it simply allows the switch to include a little jacket or a little tag, if you will, in each of the frames as it sends them to the router. And the router can say, oh, this is VLAN 10 traffic, or oh, this is VLAN 20 traffic. And then as a result of seeing that tagged information, it can go ahead and dig deeper into the packet and then perform routing based on where those packets need to go, doing its primary job as a router, which is routing packets. But by itself, a layer 2 switch has no ability to do routing based on the layer 3 IP addresses. Instead, a layer 2 switch is restricted to only making forwarding decisions based on the layer 2 MAC addresses, the ones that are associated with the network interface cards, from the devices that are directly connected to the switch, or based on MAC addresses that it's learned over, for example, an external connection or an uplink. Now, another thing that we're going to find in traditional networks with switches is we want to have remote management. For example, if this is Bob's computer right here, computer number 1, and Bob is a network administrator, he wants to be able to reach out and remotely manage a switch, we're going to need to have some IP address associated with the switch itself to allow that communication to happen. So commercial grade switches are going to be remotely manageable, and they're going to have a logical layer 3 address that can be reached. For example, an IP address. And that way Bob, using his computer and his utilities, can remotely connect to the switch, to its logical layer 3 IP address, to go ahead and interact with the switch itself. For example, to get statistics or to configure it, etc. In a Cisco environment, what we would do is we'd create a logical layer 3 address using a switched virtual interface. And depending on the vendor, it can be implemented differently. But that's the idea, is having some type of a logical layer 3 address so we can manage those devices. Now here's some exciting news regarding a virtualized switch that our ESXi hosts can support. And let's go ahead and draw a virtual switch right here. And we'll go ahead and label this vSwitch. Now on this vSwitch, we're going to have ports. And these ports are a lot less expensive than a physical switch because a single vSwitch can have hundreds and hundreds of ports. And if you need another vSwitch, you can just create another vSwitch. So with a comparison between a physical switch and a virtual switch, they both have ports. And very similar to how a physical switch works in a virtual world, if we have a virtual machine, it's got a network adapter, and we're going to logically connect it into a port on that switch. And the actual network adapter on this virtual machine is sometimes referred to as a VNIC, a virtual NIC. So when we see the term virtual NIC, that's the virtual network interface card that is part of a VM. Now, one of the challenges when we connect a virtual machine to a layer 2 virtual switch is, what if we need 3 or 4 or 10 or 50 different virtual machines all to be in the same group? Meaning a group of ports that get the similar treatment. For example, maybe a VLAN 10 assignment or a VLAN 20 assignment or certain QoS parameters. With a virtual switch, that's no problem. What we do is we can create VM port groups on that virtual switch. So if we created a VM port group and we named it prod, short for production, just as a networking label for that VM port group, we could then go ahead and associate this virtual machine with that VM port group, and then that virtual machine, regarding its connectivity to the switch, would have the same characteristics for that connection as any other virtual machines that we also assign or connect via that same port group. So as we go down our list of comparisons, the VMs have vNICs, and I'll label this as vSwitch, and let me label this as physical switch. On the vSwitch, we have port groups. And again, the benefit of a port group on a layer 2 vSwitch is that if we need 20 virtual machines to all be associated with VLAN 10, we would create the port group, associate that port group with VLAN 10, and then we'd simply logically connect those devices, those VMs, into those port groups so they could share those same characteristics regarding their connectivity to the switch. In our example we just mentioned, they could all be a member, for example, of VLAN 10. Also, on our vSwitch, we have the opportunity to connect to the outside physical world. So let's say, for example, at this port right here, we're going to use it to connect out to a physical switch. We could refer to this connection right here between the virtual switch and the physical switch as an external connection or an uplink. And when we do that, we're going to use one of the physical network interface cards, not a virtual one, but a physical network interface card that is physically part of the ESXi host hardware. So we could refer to this physical connection like by 3 different terms. We could say this is our uplink between our vSwitch on the ESXi host and a physical switch in the outside world, or at least in the physical world. We could refer to this port as a PNIC, which is an acronym for a physical network interface card on the ESXi host that's supporting this vSwitch. And we also have some naming conventions that are used on the ESXi host regarding its network interface cards that connect out to the physical world. And it refers to these physical interfaces as VMNICs. So for example, the first one would be VMNIC 0. And if we had a second physical adapter, it would be referred to as VMNIC 1, and then 2 and 3 and so forth. So from an ESXi host perspective, whenever we see the word uplink or VM NIC or physical NIC, it's referring to a adapter or connection from a physical card on the ESXi host that goes out to a physical environment, a physical network. So once again, that puts us on par with a physical switch that has external connections and uplinks, because we've got them right here too in our virtualized environment. And then last but not least, what about a logical layer 3 address? Now, an actual virtual switch that's living logically inside of an ESXi host, that virtual switch itself doesn't need an IP address. However, the ESXi host that might want to communicate with other devices, for example, our ESXi hosts all need to communicate with the vCenter server appliance. That would be really important in order for the vCenter server to manage that ESXi host. So although the virtual switch itself doesn't get assigned a logical layer 3 address for management, there is a special type of port, I'm going to go ahead and put that in blue right here, that we can configure and associate with a switch. And I'm going to go ahead and draw the blue line down here for a little more space to write. And they refer to this port, this logical port, that allows the ESXi host to communicate with the rest of the world. Using that port, it's referred to as a VM kernel port. And sometimes we also might see that as a VM kernel adapter. And as far as a naming convention, these VM kernel ports are going to be referred to as VMK something. So the first one will be VMK0, and then the next one will be VMK1, and VMK2, and VMK3. So when we see VMK anything, or VM kernel ports, or VM kernel adapters, I want you to think that's the logical layer 3 interface that the ESXi host is using to communicate with other devices over TCP/IP. And in the case of the first and foremost example, we're using a VM kernel port on a virtual switch so that our ESXi hosts can communicate with the outside network. So in our topology, we have 3 ESXi hosts, and they have an IP address of .101, .102, and .103 respectively. And what they're actually doing is those addresses are associated with VMK0, a VM kernel port that's associated with the virtual switch that they're currently using. And by default, every ESXi host, when you deploy it, creates a vSwitch, and it's called vSwitch 0 because it's the first switch. And then if we want to create another switch, we could name it whatever we'd like, including vSwitch 1 and vSwitch 2 and vSwitch 3 and so forth. So let's use this illustration to reinforce those concepts. So if this represents a virtual switch, let's say vSwitch 0, this switch is in the heart and mind of an ESXi host. So that's where this lives. And each of our ESXi hosts in the topology have each created a vSwitch 0 by default when we deployed the ESXi host. By default, there is a VM port group that's already created on the virtual switches. And it has a label of VM network. So that's a default port group that you don't have to create. It shows up by default. And again, the label is VM network. However, if we wanted to, we could go ahead and either replace that or create new port groups or both. And in this fun illustration, someone has created 3 separate VM port groups. They created one called production, one called test dev, and one called DMZ. So what they could do is they could associate with the production VM port group the VLAN of 10, for example. And that way any virtual machines that we connect to production would automatically be part of VLAN 10. For the group of test dev, maybe for that port group we assign specific quality of service parameters or certain permissions on those ports. And then all we need to do to take advantage of that VM port group called test dev is to connect logically VMs through their VNICs to that VM port group. And then they would get those same QoS or those permissions that we've associated with that port group. And the same for DMZ. Any devices that we connected to the VM port group called DMZ would get those same characteristics regarding their connectivity to the virtual switch. So if we were going to draw this to make it complete, we could have our virtual machines here. They've got their VNICs. And then we connect them logically to the port group that we want them to be in. And we don't have to worry too much about the actual literal port because it's all virtualized. So we just direct them to connect to the port group that we want them to be in. And the vSwitch takes care of the rest regarding the actual assignment to a logical port that's associated with that port group. And the question could come up, well, what if I only have 3 ports as part of the production VM port group and I need to connect another VM? And the answer is, the hypervisor will automatically and dynamically give you more ports in a port group if you're trying to connect more machines to that port group. So unlike a physical world, you don't have to worry about running out of ports, because the hypervisor is very likely going to have a higher capacity for assigning ports to a port group than you'll actually have need for. And then if we draw a physical switch out here, we'll call this, let's call it switch 1. And we have some physical connections from the physical adapters on the ESXi host to that physical switch. I'll put them in here. And I've got a question for you about these physical network interface cards. We could call them PNICs, but what is the actual labeling that ESXi gives its physical network interface cards? And I'll give you a clue. It starts with V. Do you recall what it is? And the answer is it's VM NIC. And it's going to be, for example, VM NIC 0 for the first one, and then VM NIC 1, etc. So the actual VNIC itself is what the VMs use, and the VM NICs are the physical interfaces on the ESXi host. So we could say that these VM NICs provide the uplink capability to go to the outside physical world. Or if we have two ESXi hosts, and there's VMs on each of those hosts that need to talk to each other, the traffic from a VM on host 1, for example, is going to have to go out to the physical network via an uplink, via a VM NIC, where that traffic would then go to the second ESXi host via that second host's uplink, and then the ESXi host 2 could forward that to the appropriate VM that's being hosted on that second ESXi host. And then let's imagine that this vSwitch 0 is being hosted on our ESXi 1 host in our lab environment. And the IP address that we've been using for the management interface regarding the ESXi 1 host has been 192.168.1.101. And the reason we have that is because when we first deployed the ESXi host and we statically assigned an IP address of 192.168.1.101, that was actually logically assigned to VMK0, a VM kernel port. And so this VM kernel port is associated with vSwitch 0. So one way of looking at this is VM port groups are how you connect VMs to the switch, and a VM kernel port is how we logically connect the ESXi host itself with an associated VM kernel adapter and an IP address associated with that adapter. That's how we logically connect that IP address to the switch as well. So if we were to go to a command prompt on ESXi 1, on the hypervisor itself, and do a ping of 8.8.8.8, which is an external IP address, that traffic would logically be sourced from the IP address that's associated with VMK0 in our case. And I need to pause the video right here because I just took a call from a nice young man named Logan. He's been dating my daughter, and I wanted to play just a few snippets right now for you regarding what he said. I just happened to have my mic on while he was calling, and it's pretty exciting news. I wanted to share it with you right now. Hello, this is Keith. Hey, Logan, it's good to hear from you. Going great. Good, just doing a little bit of work, keeping busy. How about you? Awesome. What can I do for you?
Well, I really love Katie, and I'm looking to get your permission to marry her.
That is an awesome idea. I think you're a great guy. I know you care about Katie. I know she loves you too, and you have my full blessing. I'm grateful that you guys found each other. You seem really happy together. Yeah, if I can be of any assistance, let me know, but that is fantastic, and I appreciate you calling to let me know. And that is my future son-in-law, it would appear, based on him wanting to propose next week to my daughter Katie. All right. And you know what? I am going to leave some of that in the nugget. So going back to our ping sourced by ESXi 1, it would be sourced from the IP address 192.168.1.101, which is sourced from a VM kernel adapter, VMK0, which has the IP address of .101. And that VM kernel adapter, that VM kernel port, is associated with the switch, which allows it to have communication to the outside world via these uplinks, which are the physical NICs, which are labeled VM NIC 0 and 1 and 2, etc. So whenever the ESXi host itself is working and interacting with the TCP/IP protocol stack, it's going to be logically associating that traffic with one or more VM kernel ports that it uses for that communication. And that could include management protocols going back and forth, for example, between vCenter and this ESXi host. And that same concept could also apply to network-based storage. For example, as we move to a data store that's reachable over the network, there's going to be some VM kernel ports on the ESXi host we're going to associate for that communication between the host and the network-based storage. And there's some other features as well, including vMotion, which we'll talk more about, which also are going to involve the VM kernel ports because they're interacting with and working with the TCP/IP protocol stack from an ESXi host perspective. And one last piece I'd like to share with you is that this is what it looks like by default on ESXi2. And here's the components. This itself, this thing in the middle, is the vSwitch. It's vSwitch 0. It's the one that the ESXi host deployed itself as part of the initial installation of ESXi. Here is a VM kernel port associated with a VM kernel adapter with the IP address of 192.168.1.102. It's logically connected to this vSwitch. And this bottom one here on the left represents a VM port group. And we've got one virtual machine that's currently using it. And that's the Linux machine that we deployed as a virtual machine in our previous nugget. And these elements right here, these are just network labels. So there's a network label called Management Network for the VM kernel port, and there's a network label for the VM port group called VM Network. And those are just the default network labels out of the box when we deploy an ESXi host. And then over here on the right, we have our connection out to the physical world. So you can imagine a physical switch out here. We'll call this switch 1. And so here we have our uplink between our virtual switch and the physical switch. We're using a physical network interface card here on the ESXi host. And ESXi is going to label those physical interfaces as VM NICs. So for example, the first one would be VM NIC 0, and then VM NIC 1, and VM NIC 2. And we could also refer to this as our external connection between the ESXi host and the physical network. So now, as a result of our time together in this nugget, if someone walked up to us and said, hey, can you tell me the difference between a VM NIC and a vNIC? We could say, yeah, one is a physical interface on an ESXi host, the VM NIC, while a vNIC is a virtual network interface adapter that's being used inside of a VM. Or if they asked us, what does a VM kernel port do? We could let them know that anytime the ESXi host itself needs to communicate using the TCP/IP protocol stack, it's going to do that logically through a VM kernel port that's associated with the vSwitch, so it can have the connectivity through the uplinks, the VM NICs, out to the external world. And in the next nugget, we'll take a look at the actual configuration and manipulation of the vSwitches in a vSphere environment. So until then, I hope this has been informative for you, and I'd like to thank you for viewing.